telescope, you use only one eye. Well, why can't you have a binocular telescope? And now we have a large one, the LBT, Large Binocular Telescope, in Arizona. And Christian's been over there to have a look at it.
This is Mount Graham, near the town of Safford in Arizona. At the top is an amazing telescope, and my guide for the journey up there is the man who built it, Dr. Jim Slagle.
Can you see that peak up there that has all those antennas?
Yep, just on the right there.
That actually goes back into the 1800s. The name of the peak is called Heliograph Peak.
Okay.
And obviously heliograph was a form of communication that the Army used, and they used it, of course, for Indian raids. And so Heliograph Peak has gone way, way back in history. We are not on the highest peak. We're on the third highest peak. And we actually did choose that for a reason. In the Native American beliefs, they believe that the highest mountain on any mountain range is sacred.
So when was the mountain first identified as somewhere astronomers would want to be?
Started in the 80s, in the early 80s, with exploration of different mountain ranges. In fact, they spent actually several years on this mountain, had a travel trailer lived through the summer and winter, looking at the state of the sky.
But it doesn't look that good today. This isn't your good season.
This is called our monsoon season, and we actually officially started last week.
So that's why we've got cloud over the mountain today.
And that's what you brought with you when you drove down from Phoenix.
Proper London weather.
It is proper London. It is.
Getting planning permission to build the telescope wasn't easy. The need to protect the Mount Graham red squirrel got the environmentalists worried and delayed the telescope for several years. But Jim's biggest headache was the road on the way to the summit.
This actually was a road that was used by wagons in the history of the people using this mountain. By the way, we've climbed 2,000 feet. That's a fairly fast climb, by the way.
Sure.
An astronomer measured, I won't say an astronomer, but I heard that it was an astronomer, counted the number of turns on this road. 523 turns. And I mean, that's a lot of turns in a short period of time. So when you ask me, what's one of your problems? When you see it for yourself, you'll understand the magnitude of getting those pieces up this mountain.
I mean, getting 2 8-meter mirrors up this road is scary enough thought.
That's why I was your height and I weighed a lot less and I didn't have blood pressure problems. So.
In all, more than 600 tons of steel for the telescope, let alone the enclosure, had to be brought up the mountain. But the telescope's complete, and Jim and I have finally come to the end of our journey.
So here we are at the Large Binocular Telescope. It's 16 stories tall, and the silver part is 12 stories tall. There's 1,450 tons of steel in the silver part that rotates, and of course this 4 stories in green here that you see is stationary building, but is central to the supplying the needs for the astronomers and also during construction.
At 10,500 feet above sea level, the Large Binocular Telescope is in a stunning sight. But it's once you're inside the building that you truly appreciate what's being built here. As the telescope moved around, all we could hear was a faint hum. Its 2 giant 8.4-meter mirrors, each weighing 16 tons, sit firmly in its steel mount. Although the telescope's operational, it's yet to gain its instruments which will sit in the center gantry. These will use light from both telescopes, and only then will the LBT achieve its full resolution.
Well, Chris, it's like I told you, 10 stories tall, and it weighs 850 tons, and it floats on oil.
The scale of it's unbelievable.
I know, and everything here is controlled by computer, so that every piece of equipment that you see on this telescope, it's all computerized. We actually keep track of everything down in the control center, from temperature to weight, any kind of measurement that you might think of, we have total control just by the computerization of the telescope.
So tell us a bit about the structure that it's sitting in, because we've got this enclosure.
All of this was made in Milan, Italy. I shouldn't say all of it now because we're refining the telescope, but the major parts of it were built in Milan. It took them over 2.5 years to build the pieces. Then they were shipped here to the United States, to Houston, where then we took it over road and brought it up here. We have a balancing system that we've just added to this. You know how many times you'd be observing, if they wanted to change an instrument, you might lose that night.
Oh, it takes hours and hours, because you need these big counterweights.
Our way of doing things is a little bit different here, and we can actually balance the telescope within 30 minutes. So we have the ability electronically, once more, with computers, of making this work. You are seeing the forerunner of the big telescopes, and we hope that all the changes we're introducing here are the things that we'll see improved upon in the future.
So the telescope saw first light in October 2004. What's happened since then?
We've had our first illuminizing, and actually we've had 2 illuminizing taking place here.
That's the coating for the mirrors.
That's the coating for the mirrors. Somebody asked me one time, they said, well, do you take the mirrors down the road when you need to have them illuminized? We only wanted to bring those mirrors up here once. The real reason why Ohio State did our illuminizing system, and so we clean the mirrors, we illuminize the mirrors, everything is done on site.
Once the doors are open, the light comes in, hits the massive primary mirror, travels up to the secondary, and is reflected back down and off a third mirror, which sends the light out onto the observing platform. And that's where light from this mirror is combined with that of its twin on the other side of the telescope. And that's the beauty of the large binocular telescope. By combining light in this way, we end up with the resolution of a telescope that has a mirror more than 20 meters across. The sun is setting, and the dome doors have been opened to let the mirrors adapt to the outside temperature. Tonight, the telescopes will be working independently, each looking at the same object, but one in blue and one in red light. Another advantage of having double vision.
So both the mirror has 2 cameras, and one is optimized for the red part of the spectrum, and the other for the blue part of the spectrum.
So we can see that here, can't we?
Yeah, exactly. These were some images taken to test the camera's performances. And here you can see the image taken, the red, here the blue, with the blue filters. And then obviously you can mesh together and stitch together the images and get the real color.
It reminds me of looking through 3D glasses. You've got a red eye and a blue eye, and you put them together.
Yeah, we do the same, but we observe with different filters, and so we observe different wavelengths at the same time.
So what are the plans for this evening?
We are testing the pointing model. We are refining the pointing model because, you know, the problem here is that we have 2 telescopes on the same mount. And the 2 telescopes should point at exactly the same direction in the sky.
And you mean exactly to some tiny fraction of a degree?
Exactly, yeah. So now we are trying to point the blue mirror to the same direction as the red mirror does.
Well, that's the plan. When we were out looking at the sunset, I have to say the weather didn't look fantastic. Do you think we've got any chance for this evening?
Well, I think we don't have many possibilities to work tonight, but obviously we wait until a reasonable hour, I think, 3.5.
Okay.
Then obviously it depends on the twilight.
The next step for the LBT is to bring its adaptive optics online. That will eliminate much of the interference from the Earth's atmosphere, making its images even clearer. There is much work still to be done on the LBT, but you can be sure, when it's fully operational, its double vision will give us a view of the night sky unlike any other.
Chris, I wish I'd been with you. Sadly I wasn't, but at least we have now the director of the LBT, Professor Richard Green, who's come to join us. Richard, welcome to the Sky at Night.
Thank you very much.
First of all, why was it decided to build a binocular telescope?
The goal was to achieve very sharp resolution on the sky. And there are 2 issues that you have to deal with to do that. One is the blur of the atmosphere, and this telescope compensates for that blur by changing the shape of its secondary mirror 1,000 times a second, and it restores the shape of the light wave coming in.
1,000 times a second?
Yes, it has 672 magnets glued on the back of a very thin sheet of glass. It's 90 centimeters in diameter and 1.6 millimeters thick, and this glass continuously changes shape.
Well, you've started your main programs. What exactly are your main programs going to be?
When we combine the two beams, we'll actually take pictures that are 10 times sharper than the best pictures from Hubble. So to use that exquisite resolution, we'll want to penetrate into the regions where new stars are being formed to learn about the disks in which planets might ultimately form and maybe even image a planet directly. We'll want to go into the bulges, the central spherical regions of nearby galaxies and count individual stars to try to do stellar archaeology and learn how those galaxies were assembled. And ultimately, we'll want to probe to farther distances and look into the hearts of quasars to see how to weigh the black hole, to see how hard it's pulling on stars and gas in its vicinity. And maybe, in the end, get out to the most distant redshifts in the visible universe and see how galaxies were assembled out of their smaller constituent parts.
First light wasn't so long ago. What are the major discoveries so far made with the LBT?
We have only these wide field CCD cameras, these prime focus imagers, and so the active groups have been working on studying galaxies that are nearby neighbors of the Milky Way in order to resolve their individual stars and to try to learn something about their formation histories. There's a population of tiny galaxies in orbit around our Milky Way called dwarfs, and they're thought to be dominated by the dark matter that we can't see. The dark matter actually binds the stars together. Dark matter almost always settles into a spherical shape, and so these galaxies are called dwarf spheroidal galaxies. They discovered a galaxy which has all the stellar properties of a dwarf spheroidal galaxy, but it's shaped like a pancake. So here's a mystery. How did that possibly happen? Because the dark matter isn't thought to be able to do that. So that was a very interesting first discovery, and that was the first paper into our refereed literature from the new telescope.
What new equipment will you use on it in the foreseeable future?
We're phasing in the equipment piece by piece at the moment, and so the ultimate achievement will be the ones that actually combine the beams from the two sides. These instruments are enormous. The principal investigator of one of the beam combining instruments has a photo of himself, and he's stretched out and he takes up about a quarter of his optical bench with all the optical elements required to capture the light from the two sides. It's our job to hold the distance that the light travels after it hits the first mirror until it gets into his instrument, which is about 24 meters. And our job is to hold that accurate to about 10,000ths of a millimeter. Then his instrument takes over and has to match up the crests and troughs of the light waves to a tenth of a 1,000th of a millimeter. So he has a little cryogenic slide trombone that moves up and down and matches the waves from the two sides to achieve the perfect focus.
It's fair to say then that this is as accurate as any telescope ever made.
That's the intention, that it is of huge dimension. It's 23 meters from the tip of one mirror to the tip of the other mirror, and we need precision to a 1/10 of a 1,000th of a millimeter when we point, when we track, when we adjust the optics.
One question I think I must ask you, everyone wants to know this. Will the LBT actually show you a planet of another star?
That's our big hope, along with our sister telescopes that combine light in a different way with the Keck telescopes and the Very Large Telescope. This one is uniquely positioned to get a wide field of view with this very sharp resolution that we complement those other telescopes.
The LBT has two mirrors, each over 8 meters across. Well, that's pretty big. Can you ever see the idea of a larger binocular telescope?
The vision to extend this design fills out the 23 meters by adding more 8.4 meter telescopes. So we have two 8.4 meter diameter primary mirrors, and they're spaced almost by one diameter. The Vision, which is called the Giant Magellan Telescope, has 7 8.4 meter mirrors on a common mounting. So in addition to the two we now have, it has one in the middle and 2 filling in the gaps on either side. And this allows you simultaneously to get the full 23-meter resolution in all directions at once, and has that much more light gathering power.
When will that come along, do you think?
The hope is that in the middle of the next decade to the second half of the next decade, these projects could be realized. But that envisions some real technical advances and some real philanthropy from both private individuals and governments to move that kind of a project forward.
When I first became interested in astronomy, the second largest telescope in the world was the Ross 72-inch at Burgh Castle.
With the 72-inch eye, the third Earl looked at those strange misty patches in the sky known as nebulae. No one at that stage knew quite what they were, and no one had ever really seen their shapes. And he found out that these nebulae were in fact shaped like spirals, and this was a completely new discovery. It was also one of the early indications that these things aren't contained in our own Milky Way, but are in fact a long way out, beyond our own particular star system in space.
And that was a metal mirror, because in those days, technology couldn't make a really good 72-inch of glass. We've come a long way since then. I wonder how far we'll go in the next 50 or 60 years.
The prospect is really stunning.
It's a great project, and so thank you so much for coming over, and many congratulations. I think the LBT will certainly go down in history. Has a long, long way to go yet. Thank you so much.
Thank you.
News notes. Well, another body in the solar system has been classified as a dwarf planet. This is Makemake. It's of the same type as Pluto, a bit smaller than Pluto, and moves around the Sun beyond the path of Neptune. You need a telescope of some size to see it. Now, why Makemake? It was discovered some years ago, soon after Easter, and then nicknamed Easter Bunny. Well, you can't have that kind of name, so therefore a mythological name had to be found, and Makemake is a creation goddess of Easter Island, so the Easter connection is still there. So we have a new dwarf planet. Welcome back to Chris, and of course Pete joining us now. And interesting things happening on Jupiter.
Yes, there are, Patrick. I mean, Jupiter is a very, very dynamic planet anyway. It's not well placed for us in the UK at the moment.
Too low down.
It's in Sagittarius and it is really low.
But it's bright. If you see it, it's obvious. It's the bright thing on the near the horizon after sunset and for much of the evening.
Absolutely. A number of people have been asking what it is, and it is that bright thing, as you say, but it is terribly low.
In this small telescope will show you the belts, and the main features, including, of course, the Great Red Spot, a whirling storm. It's persisted now for several centuries.
And the Great Red Spot is actually the cornerstone, if you like, of the story of what's happening at the moment. Exactly. But it has a companion, of course, which is Oval BA.
And it's just south of the Great Red Spot, and that means it moves at a different speed.
It moves at a different speed, and it meets up with the Great Red Spot every 2 or so years. But now there's even more interest because there is a third spot, which is known as the Little Red Spot. It's red again. It has appeared unusually at the same latitude as the Great Red Spot, and as it's travelling at a different rate around that latitude to the Great Red Spot, something untoward is going to happen because they have to meet up.
And in fact, that's just happened.
That's just happened. It happened towards the back end of June, beginning of July. The Great Red Spot was actually having one of its encounters with Oval BA at that time. I like to think of it like putting clothes through the mangle. Basically, the Little Red Spot had to slip between those two spots.
And there were very high winds there, don't forget.
Incredibly high winds, and what happened was it basically got shredded, and bits of it were seen going around inside the Great Red Spot, and then it got spat out the other side.
But it may about to have even more violent things happen to it, because it may be dropping back towards the red spot
that's
itself.
What I thought will happen, yeah. It will drop back, and then it will go through another interaction again.
Well, let's move, shall we, Patrick, from the red spots to the red planet. Let's talk about Mars.
Mars, yes. Well, all kinds of things happening there.
Yes, let's start with Phoenix. As we said last month, Phoenix is happily sitting on the northern plains of Mars, digging into the soil and looking for the basic chemistry and the history of the surface.
And it's found ice.
It has, and water ice at that.
Exactly.
This is one place we know there's water ice, and there appears to be a vast plain of ice, about 5 centimetres beneath the surface. One other interesting result from Mars, though, if you look at the planet as a whole from Mars Reconnaissance Orbiter, in this image we've coloured it so that, or they've coloured it, so that the colours reflect height above the surface. So white and red are high regions, blue are kind of below what would be sea level if you took an average across Mars. And Pete, you're an observer. You know that the two hemispheres of Mars are very different.
They are indeed, but that's quite remarkable because it really shows this the flatness in the north.
That's right, up here, and then
and the rugged region in the south.
South of the rugged hemisphere, strangely, the two largest impact basins, Hellas and Argyre, are there.
Are both in the south as well. Well, it's long been thought that one possible explanation for this is that there may have been a giant impact with Mars. So just as something Mars-size hit Earth to create the leftover material that formed the moon, Mars may have had its own giant impact in the early days of the solar system, releasing a large amount of lava and volcanic activity to resurface a whole hemisphere.
Mars at the moment is very close to the sun.
Yes, and it's dipping into the twilight.
It's dipping into the twilight, but because of the motion of Mars, we're not likely to see a reasonable view of it again for about another year, which is a great pity.
But we are getting great pictures from Phoenix, Mars Reconnaissance Orbiter. Let's talk for a minute about Mercury, because we've had a new set of results from the Messenger probe, which flew past earlier this year. And the scientists have had time to pore over the data, and there's some interesting conclusions.
A vast core.
Yes, 60% of the planet's mass is in its core, and the secret of why Mercury has a magnetic field it has no right to, it's too small to have a magnetic field, but it's there, must be tied up with that large core.
There is one theory that there's a giant impact there that stripped off the outer air completely, so all we're seeing now is the core of a formerly larger world. That's highly speculative.
I think if that happened, with the data we've got now, that must have happened very early in Mercury's history. That doesn't mean it didn't happen. It's one suggestion.
It looks remarkably like the moon, though, doesn't it, Mercury?
Superficially it does, but the surface details are different. I mean, they have what they call lobate scarps on Mercury. You don't find those.
You saw plenty of those in the Messenger images as well, where they really, really stand out. But we talked about, you mentioned the moon. Let's look at the moon itself as seen from Deep Impact. Deep Impact studied comet Tempel 1. Part of the probe smashed into the comet in a spectacular explosion, but the flyby spacecraft took images of that and is now on its way to another comet. But it's also looking back at Earth, and here's the moon transiting in front of the Earth.
That's amazing.
It's great, isn't it? As seen, it's false colour, but still, as seen from Deep Impact, it comes back round again.
Slightly sadly, that actually looks like a simulation to me.
Well, it's a long way away. It's about 30 million miles from Earth, I think, is the number. So the point of doing this is, A, it's fun and it looks great, but secondly, this is Deep Impact's mission now. While it's on its way to its next cometary target, it's studying stars to look for the brief dips in brightness that are associated with extrasolar planets passing in front of the star.
The transit method.
Exactly. You see these tiny blips and you know something's got in the way.
They are tiny blips.
Absolutely, but this is a large blip, so that you can think of this as a nearby version of the same method. So,
were the colours, by the way, correct?
no, they're not real colours in that image. This is a mixture of infrared and then blue and green.
Oh, right, okay.
So it's slightly redder than you'd expect with real colour. There is a real coloured version around, but this one shows the details of the moon much more clearly. And here it comes. You can see it just crossing Africa there.
The thing about the Earth, when you see it like this, which is remarkable, is to see that little highlight on there where the sun is shining off the oceans and the clouds.
Yeah, it glints every so often when
amazing,
it catches something. So that's the solar system news, I think. But let me tell you, I'm still not sure I believe this story. And we've got Pete here as an observer. So this is an image, I know it doesn't look like much, from the XMM spacecraft that looks in the X-rays, and it's of a exploding star, a nova in this case, in the constellation of Puppis.
Right.
Puppis?
Yes,
Puppis.
The poop deck.
The poop deck in the southern sky. Now, this image was taken in October by the spacecraft. It was just captured by coincidence. It was scanning from one part of the sky to the other, and it saw X-rays coming from this point in the sky. So they concluded it was a nova, and they've gone back and they've concluded that the explosion would have happened in June, and it would have been visible to the naked eye.
What magnitude?
5 and a bit, so not bright, but visible to the naked eye, and in fact the brightest nova of the last 10 years. And yet, not a single observer saw it.
When would it? In June?
June.
But June is not a good time, is it, for that area of the sky?
Okay, well...
Because the sun is close to Orion, and Puppis is very close.
So you would have been looking into the twilight,
It would have been in the twilight, so that's why nobody would have
They're
seen
very,
it.
very lucky to see it, I think.
Well, the good ending to the story is that as soon as they realised this was in the data, amateurs were able to go out and get observations, fill in the details of what's called the light curve, the decay from the peak, and try and understand this explosion. But I was going to criticise your observers for not spotting this, but we'll let
part
you
of Puppis
off.
is visible from here, and part is too far south. does it actually rise over here?
I don't think so. I think we're blaming the southern hemisphere people for that,
Right.
or at least those more southern than Selsey.
Now, let's come now right back near home and things happening in our outer atmosphere. Pete, noctilucent clouds.
Well, there have been some absolutely fantastic displays of noctilucent clouds. And I should explain what a noctilucent cloud is, first of all. These are very high clouds. They occupy a very thin layer of the atmosphere, about 85 kilometres up. They're about 7 times higher than the highest cirrus that you would normally see. They're supposed to be quite rare, actually, but you can't see them unless the lighting conditions are right. And this occurs when the sun is below the horizon. So there is no light coming to illuminate the normal clouds, but the light can get up to the really high levels. And when this occurs, and you've got the right twilight conditions, these clouds appear to shine in the night sky. In fact, that's where the word noctilucent comes from, night shining. And they have a sort of steely blue coloration to them. They have a lot of structure, and they're very, very distinctive.
Of what are they made?
Nobody's really sure. It's water ice in a very thin layer, but nobody's sure what's seeding the noctilucent
Well,
clouds.
there's some suggestion that they're linked to rocket launches, of all things. They seem to be becoming more common. And there have been reports
There have
of good
been
displays.
reports
Not
when-
all of them, but some of them
when the shuttle goes up, for example, there have been bright displays, but whether that's absolutely...
Reports of them go back a long way. Long
Yes,
before
not
the
all
rocket
of
age.
them. Clearly not all of them are caused by this, but they are getting more frequent, and they're fascinating.
Don't forget, it's Perseid time. The Perseid meteor shower occurs every year, maximum early morning of August the 12th.
It really is worth going for it in the early morning hours, because that's when you're
it
likely
is.
to get the best view and the most likely probability.
And something we should see well, that is the partial eclipse of the moon on August the 16th.
That's right.
80% and maximum about 10:10 summertime.
It should be quite an interesting partial, actually, because it's 80% is a big amount of the moon to be eclipsed. Do you think we're going to see colour with that?
I think we certainly will. You never quite know with the eclipse of the moon, because everything depends upon the conditions in the Earth's upper atmosphere. Because all the light reaching the eclipsed moon has got to go through our atmosphere, so it depends what's up there.
I think reddish, pinkish, but light.
Dark
anyway.
reddy brown, I think.
Dark greyish.
OK, well, we'll see who's right. But that's the joy of a lunar eclipse, is waiting to see quite what colour you're going to end up with.
And of course there was the eclipse of the sun. That was on August the 1st, only about 20% partial here. I hope you saw it, because it was total in other parts of the world. And next month we have reports of what that total eclipse was really like. And believe me, it'll be fascinating. Pete, Chris, thank you.
Thank you.
Next month we're going far beyond the solar system. We're going to look at galaxies.